Okay, good afternoon, students. We start with today's session of HPC. Am I audible? Okay. Okay, we were specifically had started with explicit parallelism. Okay. Before in the earlier lectures, we had discussed about implicit parallelism. So we discussed in details about implicit parallelism. Now we'll discuss more specifically about explicit parallelism. So in explicit parallelism, we are going to discuss about dichotomy of parallel computing platforms. Okay. Okay, is the screen visible to you? Okay. So we are discussing about dichotomy of parallel computing platforms. So in that we discussed that an explicitly parallel program must specify concurrency and interaction between the concurrent subtasks. So how is the control structure of the execution and how is the interaction between the tasks happening? That is what is associated with dichotomy of parallel computing platforms. So control structure is more associated with the program that you're going to write and the hardware that executes that program. So that is the part of the control structure, and the communication between the processors and the subtasks, that is processes, concurrent processes, is the communication between them. So the former is sometimes referred to as the control structure and the latter as the communication model. That is specifying the concurrency is the control structure. Control structure is more associated with how is the program written for that particular parallel computing platform and how is the hardware for that parallel computing platform. And the latter is the communication model, that is the interaction between concurrent subtasks. How does that happen is part of the communication model. Speaking about explicit parallelism, everybody is clear with explicit and implicit parallelism now. So you are comfortable with explicit parallelism, isn't it? So that is what we have started. The whole subject is more about explicit parallelism. Only first unit has the introduction to implicit parallelism. Remaining complete syllabus is on explicit parallelism. Okay, that is the multiprocessor system where there are multiple processors and the programs are also such written for parallel platforms. That is the concept of explicit parallelism. Okay. Okay. So speaking about the control structure of parallel programs, parallelism can be expressed at various levels of granularity, from instruction level to processes. So you can have parallelism at different levels, either at instruction level or directly at a process level. So in instruction level, multiple instructions are executing in parallel, whereas at processes level, multiple processes are executing in parallel. So parallelism has various levels of granularity, instruction level to process level. Okay. Between these extremes exists a range of models. along with corresponding architectural support. So between these ranges from instruction level to process level, there are a range of models along with their architectural support. Okay. First of all, what is explicit parallelism? Yes, what is explicit parallel? I'm again and again repeating this because that is the important part should be clear to you. Now everybody should be able to understand. I've repeated this many times. Yes, what is explicit parallelism? Yes, hardware is having multiple processors. And what about the program? And the program, what about the program for the explicit parallelism? See, VLIW is what you're talking about, Kiran. VLIW is a part of implicit parallelism. Okay, group of instructions sent from compiler to processor is a VLIW concept, very large instruction word. So that is not explicit parallelism. See, so that's still some of you are getting confused. So be clear in your concept. Okay. So you have multiple processors. Everybody agrees with that. In explicit parallelism, there are multiple processors. Yes. And what about the program? It is specifically designed for parallel computing platforms. In explicit parallelism, the program that is written is explicitly written for parallel computing platform. So the hardware is also multiprocessor and the program is also designed for parallel computing platform. So that is the concept of explicit parallelism. Okay. So the programs written for explicit parallelism can be at having parallelism at instruction level or at process level. Okay, so at maybe instructions are getting executed parallelly or maybe processes are executing parallelly on a multiprocessor system or multiple processors are present in the parallel computing platform. Okay, between these extremes exists a range of models along with corresponding architectural support. So there are different architectures which support such control structures. Okay. So control structure of parallel programs. So processing units in parallel computers either operate under the centralized control of a single control unit or work independently. So the hardware of such parallel computers either has a single control unit or has multiple control units which work independently. Okay? If there is a single control unit that dispatches the same instruction to various processors that work on different data, the model is referred to as single instruction stream, multiple data stream. So if there is a single control unit in the entire parallel computing platform, then it is called as SIMD. That is single instruction stream and multiple data stream. That means there is a single control unit controlling all the processors, but the different processors are working on different data. That means control unit is one, there are multiple processors, and each processor is working on different data. That is called as SIMD, single instruction stream, multiple data stream. Okay, and if each processor has its own control unit, each processor can execute different instructions on different data items. This model is called as multiple instruction stream, multiple data stream, that is MIMD. So in MIMD there are multiple control units. Each processor has a different control unit. Okay, so each processor will have its own control unit, and each processor is working on different data items. So that is called as multiple instruction stream, multiple data stream. Okay, so you have SIMD control structure and you have MIMD control structure for hardware of parallel computing platforms. So this is the architecture of SIMD and MIMD. Figure A gives the SIMD architecture and figure B gives the MIMD architecture. So as you can easily see, in SIMD architecture, single instruction stream, multiple data stream, there is a single control unit which controls all the processing elements, that is the processors, and they are connected together by the interconnection network. So you have a single global control unit which controls all the processing elements, or you can say processors, which are connected together by the interconnection network. Whereas in MIMD, you are having multiple processors and multiple control units. Each processing element has its own control unit, and every processor is having its own control unit, and they are connected together by the interconnection network. So this is the SIMD architecture and this is the MIMD architecture. So in SIMD architecture there is a single control unit, whereas in the MIMD architecture you have multiple control units. One control unit with each processing element or processor. Okay. So are you getting the architectures SIMD and MIMD? So SIMD has one control unit, MIMD has control unit with every PE processing element or processor. With every processor there is one control unit in case of MIMD. MIMD is multiple instruction stream, multiple data multiple data stream, and SIMD is single instruction stream and multiple data stream. Okay. Now speaking about SIMD processors, some of the earliest parallel computers such as ILIAC 4, MPP, DAP, CM2 and MASPER MP1 belong to this class of machines. So all these multiprocessors that I have told you, parallel computers, are all SIMD category computers. Okay, so all of them were SIMD processors. Okay. Variants of this concept have found use in co-processing units such as MMX units in Intel processors and DSP chips such as Shark. So co-processors were also there which were SIMD processors like MMX units in Intel processors and DSP chips in Shark. Okay. SIMD relies on regular structure of computations such as those in image processing. So image processing systems use SIMD processors. Okay, they have a regular structure of computation. Okay, it is often necessary to selectively turn off operations on certain data items. So it is required in SIMD to selectively turn off certain processors. For this reason, most SIMD programming paradigms allow for an activity mask which determines if a processor should participate in a computation or not. So using activity mask, you can selectively turn on and turn off certain operations. That means when that operation is turned off, that processor will be inactive. When that operation is turned on, that processor will be active. So depending on the requirement of the program, certain operations are turned on and certain operations are turned off. Okay. So this is an example of XIMD execution. So this is the program that you have. You have if b equal to 0, c equal to a, else c equal to a divided by b. So executing a conditional statement on an SIMD computer with 4 processors. This is a computer with 4 processors. Okay. So the A part is the program that you want to execute, a conditional statement. This is the A part, that is the program. And we have shown the execution of, we are showing the execution of that particular program. Okay. In 2 steps. We are showing the execution of the statement in 2 steps. Okay. So this is the program, and what is see what is SIMD? Single instruction. Program is one instruction for every processor, but each processor is having different data. So if you look at the processor 0 is having different data in ABC, processor 1 is having different data in ABC, so is processor 2 and processor 3. Whereas the instruction, that is the program for the all the processors, is the same. So same program instruction executed by the control unit, one control unit which controls all the processors, and each processor will have its own data. Okay. So what is happening is that initially the initial values of A, B and C you can easily see. A is having 5, B is having 0, C is having 0 in processor 0. In processor 1, A is having 4, B is having 2, C is having 0. In processor 2, A is having 1, B is having 1, C is having 0. And in processor 3, A is having 0, B is having 0 and C is having 0. So what is the conditional statement? If B equals to 0, so B is 0 in processor C, 0's data and processor 3's data. So that statement will be now executed, that C equals to A. So if you see in the first step, that is this instruction getting executed, C equal to A, processor 0 is active and processor 3 is active, storing A value into C. But since in processor 1 and processor C 2 rather, B is not 0, so they will remain idle. So in this SIMD execution, processor 1 and processor 2 will remain idle in the first step, whereas processor 0 and processor 3 will execute the data transfer. Okay, from A to C. So in step 1, processor 0 will copy 5 value into C and processor 3 will copy 0 value into variable C. So because it is executing this instruction. Same instruction is being executed by all processors, and depending on the statement, the control unit will give the execution signal to the corresponding processor which is having that data. Okay. So all processors are having different data but are having the same instruction to execute. That is the concept of SIMD. Single instruction stream, multiple data streams. Okay. Now the else part is the second step. So when b is not equal to 0, c is equal to a divided by b. So next step will execute this instruction given to all four processors. So you can easily see now processor 0 and processor 3 will remain idle, whereas processor 1 and processor 2 will execute that instruction because it is having that corresponding data in it where b was not equal to 0. So C in case of processor 1 will be equal to 4 divided by 2, that is 2. Whereas C in processor 2 will be 1 divided by 1, which will be 1. So this is a sample execution of a SIMD processor executing a conditional statement program. Getting this? So same instruction to all processors because it is having the same control unit, and each processor is having different data. So this is a sample example of execution of a SIMD processor. Yes, everybody understood this example? See, don't get worried too much about it, just the concept is important. Okay? So this is the first time I have shown you the multiprocessor or parallel computers execution. Okay, so you can easily see same program instruction by instruction getting executed by multiple processors. Each processor is having the same instruction to it through the control unit that is common to all processors, but it is having different data in each processor. Okay, the program is same with same instructions getting executed, but the data at each processor is different. Okay. So yes, everybody understood the SIMD example, and what is SIMD? Yes, be interactive so that I can understand whether you have understood or not. Okay? Okay. The next is the MIMD processor, that is multiple instruction stream, multiple data stream. So in contrast to SIMD processors, MIMD processors can execute different programs on different processors. So what happens in case of MIMD is that different programs will execute on different processors. So each processor has a control unit with it. So it can execute a program and the data with it is different. So every processor will have a control unit with it which requires program to execute and also has different data on it. Okay. A variant of this called a single program multiple data streams executes the same program on different processors. So what happens in case of SPMD is that it is a single program multiple data streams. So the same program is executed on different processors, but obviously different instruction of same program will be executed on different processors. Okay, so every processor will have its own control unit executing that program. So though the program is single, every processor is having its own control unit and processor to execute that program, and also the data at every processor will be, or processing element will be different. Okay, so that is called as SPMD, single program multiple data streams. So it is a variant of MIMD. Okay, it is easy to see that SPMD and MIMD are closely related in terms of programming flexibility and underlying architectural support. That means what? SPMD and MIMD both have separate control unit for every processor. So architecturally they are similar. Okay, and they have the same program flexibility. Only difference is that in MIMD every processor is having different program, whereas in SPMD every processor is having the same program, but every processor is having its own control unit and a processor in the processing element, and they are basically executing independent of each other. So every processing element will have its own instruction getting executed parallelly on different data. Okay, examples of such platforms include current generation Sun Ultra servers, SGI Origin servers, multiprocessor PCs, workstation clusters, and IBM SP. So the current generation parallel computing platform prefer SPMD and MIMD. So most of the current generation parallel platforms are SPMD and MIMD processors. Okay, so you can easily see in MIMD each processing element is having its own control unit. So in case of MIMD, separate program will execute on the each processing element or the processor. Okay, whereas in SPMD same program independently will be executing on each processor, because each processor is having its own control unit. Okay, getting the MIMD and SPMD concept. Every processor having its own control unit is the concept of MIMD. Either it may have different programs on every processor, that is MIMD, or it may execute the same program on different processors with its own control unit, that is SPMD. So you have SPMD and MIMD. Okay, any difficulty anybody has about MIMD or SPMD? We'll further discuss them in detail. Yes, clear with MIMD and SPMD? Okay. Yes, others are not responding. Do you have any difficulty or you are clear with the concept? Okay. Okay, SIMD and MIMD comparison. SIMD computers require less hardware than MIMD computers because SIMD have single control unit. So they require less hardware than MIMD computers. However, since SIMD processors are specially designed, they tend to be expensive and have long design cycles. So SIMD processors are expensive to design and require more amount of time to get designed. Okay, so SIMD processors are complex to design and are expensive to design. Not all applications are naturally suited to SIMD processors. So SIMD processors don't execute all the applications because they are not suitable for SIMD processors. So that is the reason SIMD cannot execute all types of applications. Okay. In contrast, Platforms supporting the SPMD paradigm can be built from inexpensive off-the-shelf components with relatively less effort in a short amount of time. So SPMD, single program multiple data streams, processor computers or parallel computing platforms can be designed more easily within a short amount of time with off the shelf components. So different components can be integrated together to create a SPMD parallel computing platform. Okay? So everybody clear with SPMD and SIMD comparison? Yes? Okay, now other thing I wanted to tell you in this session was, see there you know all know that there is a SPPU same work webinar today at 3:30 p.m. Everybody knows that, right? See, it is compulsory to attend that particular webinar. You today's and the next one also on 8th basically. I want that everybody should attend it. And what you have to do is that you have to take a screenshot of when you are attending that Zoom same webinar. So keep a screenshot with you. Maybe it will be required for you to submit that screenshot for proof of attendance. Okay? And please cooperate with us for attending the webinars because we are expected to let you and know that it is important for you. So we are answerable whether you attend or not these particular webinars because they are for your own benefit. So we have to explain to the senior management that why you have not attended and all those problems. So take care that you attend the webinars because it is beneficial to you. Okay? So take care that whenever we give you message about different webinars, they are being conducted for you basically. So it is expected that you attend them properly, sincerely, and take benefit of those webinars. Okay?